So this is the last topic. And fortunately, we're in a great situation as far as video compression is concerned, because a lot of what we need, a lot of things that would normally be pretty new at the video compression part of the course, we've sort of by accident already talked about. So we're going to cover video compression again as sort of a case study, and we're mostly thinking about it in terms of the techniques we've used in the past for lossless compression. We're thinking about it more in terms of applications. One of the reasons being that there is an entire course in ECE somewhere about video compression, and so obviously for the level of detail that you'd need for going into great depth about different schemes for video compression and specifically what schemes do as opposed to typical techniques, we have a course for that already, so we don't need to duplicate much of that here. So the first thing we should probably observe is that ultimately a video is a sequence of still images. The way that we conceptualize video, and that's true in the age of digital video, but also is true with analog video, is that it's a sequence of still images, and that our human visual system will perceive movement if we switch images in a certain way and we do it quickly enough. So if we maintain a certain frame rate, then generally our brains will believe the illusion of motion. And that frame rate can vary. Film, for example, is typically displayed at 24 frames per second, and television signals are typically displayed at 30. Some television can be displayed at 60. Most people, among people that use computers for various graphics-related tasks, nobody in particular, but there tends to be some debate about whether we want to have frame rates that are egregiously high, so 150 or 144 or something, but for the most part, all the monitors that people use generally constrain the actual number of transitions per second to 60 hertz, so 60 frames per second at most. In any case, we're going to think about video usually as a reference point as being displayed at about 30 frames per second. So a video is a sequence of still images. So we could, if we wanted to, compress video, we could just take every frame of the video sequence and compress it like a JPEG. And there are reasons that this is actually relevant, like we might want to do this. We know that JPEG compression, or whatever, some scheme similar to JPEG, a lossy image compression scheme, is pretty good, so why not just apply it to every frame? It's fast. Well, the problem is, if we begin to think about the actual, the numbers there, it doesn't seem like we get enough out of that. So a single frame of 1080p video, if we store it in RGB, requires about 6 megabytes. Okay, great, but we're past that. We know already that we can sacrifice some stuff, and if we're going to compress each frame individually, we're going to do this. We might store it in 420 YCbCr, which means we end up taking half the space. We keep Y at the full resolution. We degrade CB and CR to 1/4 of their original resolution. It turns out that sort of neatly ends up taking exactly half of the original amount of space. If we compress each frame using JPEG, then we can usually expect, this is a rule of thumb, we're going to see a few of those today, we can usually expect that we could get that down by a factor of 10 without really seeing any quality degradation. Now, keeping in mind, we probably have a much higher tolerance for quality issues in video because we don't even look at each image for long enough to go searching for artifacts. We need to make sure that whatever artifacts exist ideally aren't obvious, and that is to say that they don't persist in every frame. So we don't want every frame having the same artifact, because then we could stare at it for a while. We also don't want an artifact to be so glaring, to suddenly appear and then disappear, that we notice the sudden change. But we could probably degrade quality further. We could, maybe 300K per frame is a little bit high. We could even go lower than that, because we don't need to keep JPEGs at with no perceivable quality difference if we're only seeing them for 1/30th of a second. But if we follow the numbers with a 300K, we can see why we're still short by quite a bit. So if we use 30 frames per second and we compress each frame with JPEG and expect it to get us down to 1/10 of its size, so 300K per frame, we're looking at 75 megabits per second. So 9 megabytes, 75 megabits per second. If we do, so this is 1080p. Which I think in 2020 is sort of a reference standard for high quality video. Much of the video that you watch, YouTube or Netflix or whatever, is likely not transmitted at 1080p. But suppose that we look forward, we look towards the future, and we take that as our reference point. 75 megabits with JPEG compression on every frame. That's not happening. If I use 720p, that's 33 megabits. And how can I expect a sustained connection with that throughput over the internet? And there's also the matter, as I mentioned at the very beginning of the course, that it's one thing if your connection can give you 33 megabits, but if everybody is streaming video at that rate from one server, there's no way the server has enough bandwidth to send that amount of data to so many different places. And we saw those articles on the first day of class that, because of compression technology, the internet will barely be able to survive the massive bandwidth increases demanded by people all staying home due to COVID and watching Netflix. So we need to do better than 33 megabits per second, even if we have a connection that's that fast. So I went looking. It's hard to find this. We'll see in this lecture, we actually have difficulty getting concrete sources for recent information because a lot of it is now less the subject of academic research where you could cite a publication and more a matter of trade secret. So it's proprietary information that nobody sees, either nobody wants to share or nobody sees any reason to share. But an example as a guideline, if you go looking on YouTube for what they think high-quality video looks like in terms of bit rates, they say, 8 megabits per second for 1080p 30. And that, so, consider that. That's less than 1/8 of this value, 1/8 of what we have if we use JPEG. And we could degrade the JPEG quality further, but there has to be some middle ground. And then 5 megabits per second for 720p. The issue we have to consider here is that 2 consecutive frames of a video, I don't even care what kind of video it is, whether it's actual full motion video taken by a camera, whether it's animation, whether it's CGI, whatever. 2 adjacent frames in a video that are showing up 1/30th of a second apart are probably really, really correlated. They are highly correlated, and so we should begin going after similarities between 2 frames, just like we went after similarities between 2 adjacent pixels in an image. And the question then becomes, how do we do that? And it's true that we could, I suppose, in an extremely, if we view the problem explicitly mathematically, we could say there's frame 1, and then in the future there'll be frame 2, there's frame 3. So really, instead of a 2D array of data, we have a 3D array of data. I suppose we could do a 3-dimensional discrete cosine transform, but we can see that there are some practical challenges to that. So one of them is, although it's true that, yes, I could just interpret all of my data as one massive 3-dimensional array, I do want to be able to decode a stream that might be 72 hours long, and I want to get it frame by frame. I want to watch live TV, basically. And that's significant because digital television uses video compression. One of the reasons that we've transitioned from analog TV to digital TV is that by using clever video compression, we can actually save physical, literal spectrum bandwidth. The actual sets of frequencies we need for television transmission have been reduced by converting to digital, and we can then reuse those frequencies for things like cell phone networks. So the ability to do video compression for literal live transmission, so that is to say, I encode a frame of video and you decode it half a second later, thousands of kilometers away. That's something I should expect to be reasonable. Maybe it's true that it takes you 1 second of latency to actually decode live video, but it needs to be live enough that for example, if I had a television program, you could call into it. Or if I'm streaming data over Zoom, you can ask me questions in more or less sort of awkward real time. There'll be small delays, but we expect to be able to encode and decode almost simultaneously, separated by some channel with some delay. So I need to do that. So obviously I can't just apply the same technique I would apply to an entire image, to an entire stream of video. I may therefore want to keep all of the frames separate. It's reasonable that I guess I'm willing to consider a frame as a unit of data. I don't need to see at a subframe level. It's okay if I wait for the whole frame to be received before I decode it. There are some other constraints that we have to consider. And so one of the big ones is, unlike image compression or anything else we've dealt with so far, if, for example, Deflate or JPEG, if you send me an image and for some reason the first half of the transmission gets lost, then I assume that's a write-off and I ask you to send it again. If I'm downloading a zip file and half of it gets lost, then the zip file's corrupted and I can't see it. Then I ask and I go get it again. The thing is with video compression, again, think about live television, I might tune in halfway through the broadcast. I want the ability to join the stream, to pick it up halfway through, even if I've missed the first half. Maybe I'll never get the first half back, but I want to begin watching as soon as I tune in, or, within a couple of seconds of that. That's a constraint that's sort of unique to streaming video or streaming audio, and we have to talk about that. It turns out it's not actually, once we get there, it won't be very exciting. There's a pretty obvious thing we have to do. I want to talk about some history. So this is annoying because there's some interesting history here, but just like I mentioned a few minutes ago, video compression itself is largely shrouded behind lots of patents and trade secrets. And some of the best video compression schemes that appear to be in use aren't really well described. So I can't say much about them because there's no published document about them, because if you've developed your own in-house compression scheme, why would you bother publishing an academic paper about it? And I mean, more importantly, even if you thought it was a good idea, who would, pay you for the time to do that when the goal of your organization is to stream video? So I want to talk about this family of schemes called Mpeg, and they're not really a family in the sense that the LZ family, like LZSS or LZ77 is a family. They're a sequence of standards by the same organization, and they use similar techniques, but it's not like they're all the same technique and developments of it. They're just different standards documents. And the problem with the Mpeg schemes is that they're all, there's just patents all over the place. They are encumbered by hundreds of different patents, which means if you want to use Mpeg in a product, you probably will have to pay royalties if it's a commercial product, and if it's non-commercial, you're still in some jeopardy if your code is public. And there's been some, over the years, it's been difficult to know whether it's actually possible to publish the code to Mpeg encoders and decoders in all cases. The piece of software we're going to use for assignment 5 does support Mpeg encoding and decoding, and they don't really seem to care that much. That wherever they're hosting the code, maybe it's out of the jurisdiction where anybody would bother suing them. It's also true that because of the way patent law works, it's not really, you haven't broken any rules until somebody presses charges, so maybe they're just hoping nobody cares. In any case, I want to talk about these schemes because they are a running thread, and because all of the institutionalized video compression that we see, so digital television, streaming on YouTube for the most part, and things like Blu-ray disc, if anybody cares about those anymore, or DVDs, they all use Mpeg schemes. And that's because it is a widely understood standard. It's a standard, a set of standards that are implemented in hardware, which is a big deal for high-definition encoding and decoding, and so they're widely supported. I don't want to make it sound like I'm only talking about them because they're the ones that people have to pay for. I actually personally, my interest into video compression came about as part of interest in open source video coding, and it's unfortunate that I can't really talk much about that because it's hard to really define these systems, and because they develop quickly and there's no real standards document. Any of you that have contributed to open source projects know that typically the focus is on getting the code written, and there are requirements involved, but there's typically no time when people sit down and format a standards document. And we've seen with things like Deflate or bzip, there's an RFC, there's the manual, a description of how the format works, but no standards document. So I want to talk about the Mpeg schemes, and I'm going to start with Mpeg-1. And the techniques that we're going to cover in the rest of this lecture and the course are basically all stuff that's in Mpeg-1. The improvements made on those schemes are either so complicated that we don't want to touch them, but there is a separate course that ECE offers that talks about them, I assume, or they're just developments of the Mpeg-1 schemes in such a way that by implementing the basic version, we understand a lot about how the advanced version would work. So Mpeg-1 was formalized in 1993, and my understanding is that actually they had to rush it out the door because the draft versions were already being implemented by manufacturers of hardware. Like, they were so eager to get their hands on it that they were implementing it in their hardware before it was even standardized. So they just ran it out the door in 1993, and they rolled over whatever they hadn't agreed on yet to become what was called Mpeg-2 later. So the goal of Mpeg-1, and these original schemes were designed for very specific things. Schemes these days are designed to compress video at any number of different resolutions for any number of different reasons, whereas Mpeg-1 was designed for a very specific concrete purpose. They wanted to compress VHS quality video. So I mentioned before that in the 90s, if you wanted to record a TV program, you'd use a videotape, and it would be, in North America, you'd probably use a VHS tape. They wanted to compress VHS quality video, which is analog, so we can't say very much about its frame rate or its resolution, but let's use as point of reference what Mpeg-1 did, which was in North America, it would be 352 by 240 resolution. And I mean, think about that. That's tiny by modern standards. That's VHS quality at around 30 frames per second. The actual nominal frame rate of color television in the analog age was 29.97 frames per second. In the old black and white age, it was exactly 30, and they did some tricks to make it 29.97 to cram in some extra color information in the standard that we used for analog color television, which I think came about in the 1960s. In any case, Mpeg-1, let's simplify it down to Mpeg-1 wanted to compress video at either this or this resolution, depending on if you're in Europe or North America, at either 25 or 30 frames per second. And there was an audio track as well. Now, we're going to ignore the audio problem because we don't have time. Audio compression is lots of fun, though. So they wanted to compress it at a bit rate of about 1.4 megabits, so for both audio and video. And I believe, offhand, I think that the video bit rate was about 1.1 megabits. So the other 300 kilobits was for audio and for sequencing metadata and things. And the reason that they specifically were working with this resolution, this frame rate, and this data rate was because of constraints. One, they wanted to create a format that would allow video to be stored on CDs. So they wanted to create the video CD, which did exist. Nobody really seemed to care that much, but it did exist. The typical data rate of a CD player was nominally 1.4 megabits per second. So they wanted to, on the cheapest possible CD hardware, they wanted to be able to store video. And so the CD hardware, the nominal data rate of 1.4 megabits is the rate of uncompressed audio CDs. Now, of course, there were eventually CD drives that could read data far faster than that off of a CD, but they wanted to be able to work with standard CD players. The resolution was because they wanted to compete against the other standard for videotaping, which was VHS. So that was it. That was the humble beginnings of standardized video compression for the domestic market, and it was called Mpeg-1. Later, this was followed up by something called Mpeg-2, and you've seen I actually made a mistake in the resolution here. It's 720 by 480, as you can see here. And the idea behind Mpeg-2 was to be able to transmit at what you'd consider a standard definition television signal. So if you were receiving cable television in the 90s, analog cable television, and you saw a high quality signal, the actual nominal resolution of color television was somewhere around 720 by 480 pixels, with a few extra pixels on the side that were often discarded because they were never actually seen on the screen. So the frame was nominally bigger than that, but the viewable area was considered to be at most 720 by 480. The standard was eventually called Mpeg-2, and it contained a lot of other improvements on Mpeg-1 because, again, Mpeg-1 was run out the door, and they tweaked it a bit. I think Mpeg-2 came out a couple of years later. Mpeg-2 was ultimately used for DVD video and by digital broadcast television at standard resolution, and that's still the case today. We are using typically, these days we would use Mpeg-4 for some transmissions of HD. Not all. A lot of HD video is still transmitted in Mpeg-2, but standard definition signals are typically transmitted in Mpeg-2 even now. So that's one reason why the Mpeg standards are worth covering, is because they are in use all the time, even today. A typical Mpeg-2 stream, so Mpeg-2 was designed to maybe work with different resolutions, but typically it was designed for, the normal profile was 720 by 480 pixels at 24 or 30 frames per second. And we would typically call that 480p in today's language. Now, one thing that I would love to talk about, but that we don't really need to worry about these days, is that it turns out that actual television signals in the analog era were transmitted, again, at that funny frame rate of 29.97 frames per second. Now, if we ignore that problem and just say that that was 30 frames per second would be received, but actually the effective amount of information amounted to 60 frames per second at half the resolution. And what I mean by that was that one frame of analog NTSC video would be encoded in an analog sense by the following process. First, every second line is captured at one interval of time. And then that's encoded as let's say the even numbered lines of the frame. Then a tiny amount of time later, so 1/60th of a second, every alternating second line is encoded. So there's these lines here are encoded into the same frame. And so what you'd end up with is actually two moments in time sequenced into the same frame of video interlaced. So the term interlaced means each line comes from a different moment in time. And so the way this would work on a video display is your television would then display alternating lines from the first moment in time and then go back up and display the other lines. And so it would undo that process. And so actually it would display at an effective rate of 60 hertz, 60 apparent frames per second, or 60 fields per second to differentiate against the pictures that were received. But they were actually interlaced frames being transmitted at 30 frames per second. Now that's interesting in the sense that it actually it creates the illusion of more resolution than really existed there, because you'd actually only get 240 lines of resolution per field. However, because we no longer need to worry about that, because these days we do just transmit actual frames, not some weird interlaced thing, we're not going to worry about it. Although if you ever see references to things like 480i or even 1080i, it's because of this old interlaced convention. Now, we're not going to worry about it. We're going to think about what's called progressive scan video, which is, for some reason, that's called progressive. But what it means is literally the whole frame is displayed at once, not this funny interlaced business. So 480p is, let's say, 30. So if I were to write something like 480p 30, that's normally interpreted to mean 480 lines of resolution, 30 frames per second, and the P means each frame is displayed entirely once, as opposed to in an interlaced format. So basically 480p means 480 lines of resolution at 30 frames per second displayed exactly as you'd expect video to be displayed, the same way that film is displayed, one complete frame at a time. And then we'll leave it there. We won't worry about interlacing any further. The book talks about it at great lengths because early video compression standards had to somehow work around the strange issues that could occur when compressing interlaced video. So the Mpeg standards don't just talk about video, they do talk about audio, because again, the goal of Mpeg-1 was to actually compress both video and audio into the data rate of a CD. The Mpeg-1 audio format, which was ultimately not really used for DVD video. So Mpeg-2 was used by DVDs, it was also used by broadcast digital television. Mpeg-1 and 2's audio format was largely not actually used by a lot of the video compression schemes that ultimately used Mpeg-2 video, including things like DVDs. They would use, DVDs would typically use a codec called AC3, which was due to Dolby, which supported 5.1 surround sounds, which is one reason it was used. And so it turns out that the Mpeg-2 standard contained this strangely labeled, and we'll see that the labeling inside of Mpeg standards becomes a bit nonlinear here, but inside of the Mpeg-2 standard is an audio format. There are actually several audio formats. One of them is called Mpeg-2 Layer 3. And somebody noticed that this was actually a really good audio format, and they found a way of just encoding it by itself. And we call those files MP3 files. And that is where the MP3 format came from. It was dug out of a video standard somewhere else. And it turns out that the normal Mpeg audio is not MP3. MP3 was defined as an advanced profile audio format inside of the Mpeg-2 standard. Even though it's called Mpeg-3, it's actually from the Mpeg-2 standard. And for whatever reason, it wasn't really adopted by any of the, by DVDs or broadcast television. They use other audio codecs instead. So there was no Mpeg-3, or there was a document called Mpeg-3, but it didn't actually cover video compression. It covered some, I think, some structural aspect, like how to transport video or something. So the next document was called Mpeg-4. And after that, naming became completely meaningless. And we'll see even Mpeg-4 is sort of a meaningless name. The Mpeg-4 standard described a whole bunch of different stuff, including audio compression schemes. One such audio compression scheme is used today called AAC. It describes several video compression schemes, of which we typically only talk about one of them as being called Mpeg-4, and that is Mpeg-4 ASP. The Mpeg-4 standard came about in about 1999 and 2000. The first implementations of Mpeg-4 ASP were due to as with any other standard like JPEG, there was no necessarily specific code base that anybody would work with. It was a description of how the decoder was supposed to work. Even Mpeg-1, there was no reference implementation. Instead, the standard said, here is what the bitstream looks like, here is what the decoder does to decompress the video. And then it was up to you how to write a decoder that did that, and then write an encoder that produced data in the right format. Early compression schemes for Mpeg-4, Microsoft designed one. There were a variety of others that were designed. They were eventually picked up by an open source project. Well, a short-lived open source project called DivX existed, and then it became a corporation, and I think they may still exist. They may still be working with the same sad Mpeg-4 codec they had 20 years ago. For the brief period of time where DivX was open source, it was captured by this other project that created a fork, and it called itself Xvid for obvious reasons, because it was actually a fork of DivX. It was developed for quite a while, and it was used for early Mpeg-4 video, although at the time there wasn't much of a market for Mpeg-4 video, because when would you work with digital video? This was before the age of YouTube, and if you had a digital cable box, it was using Mpeg-2. So if you used Mpeg-4 back then, you were either working with some primitive streaming app of some kind, or maybe you were working with video files. But I know that just like how MP3 heralded the beginning of file sharing for audio purposes, so you might remember there being there was a movie made about this too. This service called Napster in about 1999 or 2000. I still remember using this when I was I don't know, I was in school of some kind, elementary school or something. This service called Napster, which would allow people to share MP3 files, because whereas a 3-minute clip of uncompressed audio might require 40 megabytes, a 3-minute clip of MP3 audio in very high quality might require 3 megabytes, which was well within the ability to share back in the age of 56K dial-up modems. And so, while this MP3 format heralded the beginning of audio file sharing, this format here, so Mpeg-4 ASP, and in particular these two codecs, heralded the beginning of video sharing. So I remember I have vivid memories of entire feature-length films being available and in file sizes that were within the ability of my internet connection to download in, I don't know, 2002, 2003 or something. And so I think some of the ability for the, I don't know, 2000 era films like The Matrix or something to actually be encoded into the size of maybe just a CD's worth of information was a really big deal. And that's where these began to catch on. But I guess it's strangely, even though this heralded the beginning of a lot of new thinking about video compression being useful for actually being able to watch movies using the amount of bandwidth people had back then, it wasn't until later that it actually caught on for streaming purposes. YouTube didn't appear until, 2005 or 2006. And there haven't, and since then there have been a lot of other developments, one of which, a huge one, is elsewhere in the Mpeg-4 standard. There was this thing defined called Mpeg-4 Avc. It was also standardized under a different name, H.264. So this is a different standardization body, I think ITU or something. Standardize it this way. And Mpeg-4 Avc, which required a great deal more computational resources, but also produced much better encoding, eventually caught on and has been adopted by now as the current sort of reference standard format to use for high-definition video and streaming. And remember that we have better codecs now, but there are also processors that are made, right? Like most processors that you've been able to buy for the last few years actually have hardware extensions just for decoding this kind of video. And so it's really attractive to use this format because even a low resource CPU can do this decoding because of the built-in hardware acceleration. And so that's a big deal, and that's one of the reasons why that's still used for streaming now, even though there are more advanced techniques that have existed since then. And I think, as I said, I can recall, downloading full Hollywood movies at about 700 megabytes a piece in this format, and I can recall a time in, I don't know, the late 2000s or so, where suddenly the format switched over to being H.264 as there became more widely available H.264 codecs. It turns out there's a successor to that, and of course names have gone off the rails here because both of these things are Mpeg-4, and yet we only call one of them Mpeg-4. We typically call this is typically, if somebody talks about Mpeg-4 video, maybe they mean this. Usually we just call it H.264 instead of saying Mpeg-4 Avc. There's a successor called HEVC, which is currently beginning to displace other formats as competition to AVC or H.264. The problem is that it's still relatively new, and so it takes a while to actually build up that momentum, in particular because there's lots of devices that have been designed in hardware to decompress H.264 video, and it's going to take a while until this format catches on. But it appears as of now, as of the last week or so, it does appear from the research I've done that it is basically now in second place, which is sort of nice. But its formal name, of course, is something Mpeg-H. We've just given up on the numbers. We still call it Part 2. I don't know what Part 1 is. Okay, the thing about the Mpeg standards is it's a good history lesson. I think it's great to watch how they've evolved over time, and they're supported widely by devices, and most actual general-purpose computing devices have processors or video processors in them that can do some of that decoding in hardware. However, they're encumbered by all sorts of patents. And that means if you're developing a product that needs video and you use Mpeg or some derivative of Mpeg, you might end up having to pay royalties, which is no good. And I use the term here, royalty liability, because maybe you may not actually know whether there are patents on a particular thing that you're using. You won't find out until somebody sues you in some cases. You might get a cease and desist letter saying, sorry, your product that you're currently selling includes stuff that we have patented. Either you pay us or we're taking you to court. That's a bit of a rough place to be if you're, running a startup or something. And so one option would just be to grit your teeth and pay the royalties. Just do it from day one. You don't know if whatever scheme you're using is actually part of an Mpeg patent, and so just begin paying the Mpeg royalties. They have a scheme set up where you can just pay royalties to a single organization or whatever, and they fan them out as needed among all the different patent holders. But it's worth considering that there are lots of royalty-free schemes that have gained widespread support. This one's old and not very good, but it was the first example of a scheme that was previously patented, and it was opened up, so all the patents were not relinquished, but a royalty-free license was granted to everybody that used the scheme. This scheme called AV1 is catching on. And it's actually based on some of the same ancestors as this format. And AV1, as of this year, appears to be open, although even that's a bit tough because these schemes are so complicated that there could be people out there that hold patents on part of it that just aren't coming forward. And we won't know until a certain amount of time has passed. So patents have a certain expiry date, and so we know if the scheme has existed for a certain number of years, anybody who held patents on part of it would no longer do so. We haven't reached that point with AV1 yet. I want you to come away from a course like this believing, though, that if you ever need video compression, you don't necessarily have to turn to the Mpeg standards. There are lots of other options that are truly open source and actually free, not just free in the sense of both free beer and free speech, which is important. But we can talk about Mpeg because they're well documented and they're widely used. There's also this, which is that if you go work somewhere that works with streaming video, they may well be using a standard or a codec, a compression scheme that they came up with themselves that nobody else has ever heard about. And so I have no way of knowing about those. I can't talk about them. And even if I did, even if I'd been involved in one of these organizations that works with video compression, I would have signed an NDA, so I wouldn't be able to tell you anything about it. I'd have to pretend like they didn't exist. So as a result, we're of course not going to go deeply enough into video compression to care that much about these nuances. We're going to pretty much only talk about the basic stuff. But it's worth considering. I really don't want people to get the impression that you have to go with patented software designs. I have complicated opinions on software patents. It's worth considering that for the most part, even the most advanced schemes, that includes HEVC and AV1, use DCT or something very similar. So maybe the discrete sine transform. One thing we didn't talk about in this course was a concept called a wavelet, which can be used for compression, including image compression. And there are image compression schemes out there that use wavelets, although they haven't been able to displace JPEG. For some reason, none of the schemes used widely now do use wavelets, although there are quite a few that exist that use wavelet methods. One of them is VC2, or Dirac, which is developed in-house by the BBC, it turns out. But now it's an open standard, and it uses a wavelet-based method. So there are other options. We'll constrain ourselves to talking about DCT-based things because we've only heard about the DCT in this course. The other thing we have to do is prune down what we're going to talk about in terms of compressed video transmission. There's a lot of complexity that goes into taking this long set of frames, millions and millions of frames of video, and then compressing it in such a way that you receive it basically in order, more or less, plus or minus a few frames. and that you can decompress all the frames and display them as you're still receiving part of it. And also there might be audio. I need to make sure the audio is synced up to the video and that you receive enough audio and video in each second to be able to keep playing them back continuously. That's really complicated. So normally if we have compressed video, we don't transmit it on its own. We instead package it up somehow. We might call that, if it's a file format, a container, just like with gzip or whatever, or a transport stream. They're typically interchangeable. A lot of container formats are designed to be streamed, so you can send the container format from beginning to end in such a way that you can decode it from beginning to end. That makes sense because even if you have it as a file on disk, you want to just read the file from start to finish. You don't have to skip around in the file too much when you're reading it. Container formats typically provide you the ability to take a variety of different video streams, maybe more than one, and audio streams, maybe more than one, and other data like subtitles, and multiplex them together. And that's complicated, and it actually constrains the way that the video format works a bit, which I'll talk about in a minute. But anyway, the formats you might see in use, you probably have seen videos in these formats, MP4 or .m4v. That's a raw container format, or relatively raw container format defined by the Mpeg-4 standard. MP4 would be an Mpeg-4 video and audio stream multiplexed together. Usually you use M4V for a video stream by itself and M4A for an audio stream by itself. You might also see .AAC, which is AAC being one of the codecs defined in the Mpeg-4 standard. This is a container that's caught on in the last, 12 years or so. I remember first seeing this container format when I noticed that if I wanted to download episodes of TV shows in 2007 or 2008, one day they were in this old .avi format that was used on Windows, and that was when they were using Mpeg-4 ASP. And the next day they were in this format because they were using AVC, so H.264, which for some reason that didn't work well with the old Windows AVI format. Those of you still using Windows may notice that for some reason .avi is still used on Windows. It's an ancient container format that has a lot of weird limitations, but you can still use it, and there are reasons why a lot of pieces of software do still use it, sort of for lack of an alternative. If you're on Mac, you might see this .mov, which is the QuickTime format. It actually ended up being, I believe it was used as the basis for this format at some point in the past. So we're going to use an extremely raw format for our assignment 5. We're actually going to take videos in a more complicated format and use a different program to dump them into an extremely raw representation where all they are is color planes as flat arrays. So all of the Y data, then the CB data, then the CR data for each frame in order. That's it. That's not practical, but we don't want to spend time worrying about container formats. We would much rather worry about the actual compression. Now, what's interesting about container formats is the restrictions that they impose on the video stream can affect how the video stream works. Oh, there it is. Yeah, I was wondering where that slide was. When you use a container format, the container format specifies a particular way of packaging the video into chunks so that we can alternate between video chunks and audio chunks. And that can actually affect how the scheme works, because we have to make sure that the data in the chunk can be packaged up as far as the compression scheme is concerned. That means that there are cases, like I mentioned a minute ago, where H.264 doesn't work with the AVI format. There have been cases where some video formats don't work with some containers. Even though the container could be purportedly general, it may not support certain formats because of internal limitations. That's one more reason we don't want to worry about a container format. So I'll post a second video where I show off the basic format that we're going to use and how to use it and how to play back the videos. I've worked out a way of making it possible to stream those videos even if we don't need to use much infrastructure in our programs to actually work with the data, so we get the best of both worlds. If you wanted to use a formal container format, you'd have to use some pretty bulky extra libraries, and it would require quite a bit of fiddling around with different objects inside of the libraries to actually get video data. So we're only going to discuss some basic techniques used by video compression schemes for the sake of flavor, essentially. These are all techniques that actually were used in Mpeg-1. Although it's true that they weren't used to the extent that they're used today, and in some cases they weren't supported at all by actual compressors and decompressors. Now, we've talked all the way through the JPEG and ordeal, and we know that the JPEG standard was full of all sorts of interesting things that weren't really supported by any compressors or decompressors. The same was true of Mpeg, is that once the standard existed and we had some idea of what constituted decent compression, actual implementers of it went and chose the parts that gave them what they wanted and ignored the rest. So we're going to talk about basically these things. Macro blocks are an incremental step. Temporal compression is how do we leverage the fact that two adjacent frames are similar to each other. Motion compensation is how do we account for the fact that if I have, let's take a look at a frame. Here's a frame and here's the next frame. The frame might depict movement or something. So this piece of this frame might not look very much like the corresponding piece of the next frame, but it might look a lot like this other piece of the next frame because the frame has moved. There's motion. And so motion compensation is looking at ways of leveraging that for better compression. And so we'll talk about those things, and the goal of assignment 5 is basically to take what you had from assignment 4, which is the still image part of this, and generalize it to compress streams of images for video streaming. So the first thing is, back to my example from earlier, the most basic way of compressing video just takes each frame and encodes it as its own image. And so I've got 7 frames here. I send you the entire set of DCT coefficients for each block in image 0, and then I start again for image 1. I get 7 completely independent images. And for the sake of terminology, it's important to understand that even if we do this, we still get compression because I can compress each image with an image compression scheme. And so I'm only allowed, if I do it this way, to use, when I'm compressing, let's say, frame number 2, data from frame number 2. So I'm allowed to use the data inside the frame to compress the frame. I'm doing what's called intra-frame compression. As opposed to inter-frame compression. Inter-frame compression is where I use data from one frame to help compress another. Intra-frame is where I only use the data inside of that frame. Now, both inter and intra start with I, and yet for some reason, we use the term iframe to refer to a frame of video that is only compressed using data from inside of itself. It relies on no other information. That's helpful in a stream, even if I have other options. It's nice if I have that because suppose for some reason I only tune into the stream around here. And the first frame I receive data for is frame number 3. Because frame number 3 has only been compressed with data from frame number 3, I can decompress it without knowing anything from the past. So that's nice. Iframes are useful even if I have other options because they allow me a way of restarting the decompression process if I tuned in late. So in all major video formats, I can expect that there will be at least one iframe. Generally, there are a lot more for reasons that we'll see later, but there's going to be at least one. And it'll usually be the first one, although we should think about that a bit. Yeah, this is pointing out what I just said, but we want to save, obviously, we want to reduce bit rate. And we've seen that if we compress each image independently, we're going to have a high bit rate. That's no good. We need other options. But on the other hand, there are use cases where bitrate's not a big deal, video editing being a big one. So if I'm editing digital video, it's nice to have each frame stored separately so that dependencies between frames don't get in the way of what I want to do. An example being, if this frame depends on, I don't know, this frame back here for something, so if it's not an iframe, and I cut the video, I don't know, here, I've got a problem. I've got to reconstruct this frame before I can recompress it. If instead every frame is independent, every frame is an iframe, and I just cut the video arbitrarily, who cares? I just discard all these other frames and it's no big deal. So there are lots of reasons for things like video editing that having only iframes is fine. And there are codecs that exist that only compress iframes. There's actually a codec called MJPEG or Motion JPEG, which just compresses each frame to a JPEG image. And those are valid, but they don't give us the bitrate advantage that we want, and we can see, as we've been looking all semester, we can see a source of redundancy to eliminate. Two adjacent frames are similar. Let's find a way of reducing the information so we don't store the same thing twice. And the slides agree. Since two consecutive frames often have significant similarities, not always, but often, why don't we basically use delta compression? I mean, and again, it's interesting how a lot of these techniques from May are suddenly bubbling back to the surface. I know that likely, in a typical video, frame 3 has a lot of similarities. I mean, an example being, if I am pointing a camera at a particular background and people are moving around at the front, some pixels will be basically identical between frames. So why don't I take, okay, I'll encode frame number 2 fully, and then I'll encode frame number 3 as just a bunch of delta values from frame 2. And the hope is that the more similar the two frames are, the smaller those delta values are and the more compression that I get. And so we get what are called p-frames. And this is a form of temporal compression. I'm compressing over time. And if I use the most basic form of that, we formally consider that a form of prediction. I'm predicting the value, so here are two adjacent frames. And if this frame is a p frame and this frame is an I frame, then the value of the same pixel in both frames can be predicted by saying, okay, I'm going to assume that the value of this pixel is some multiple, or it's this pixel plus something, plus a delta value. So I'm predicting the value of the pixel here using the value of the pixel over here. And so a p frame is a frame where the contents are, at least in part, but maybe entirely, compressed by predicting them based on data from a previous frame. Now, to be clear, usually in most systems, and certainly in the one you define on assignment 5, it's fine if on a per block basis, some parts of a p frame are still stored fully. They're not stored as deltas. But using a p frame allows us to leverage data from the previous frame. And so we'll model it on this diagram with this dependency. So in general, every p frame depends on the previous frame. Now, more advanced techniques, so H264, for example, actually allows you to have a frame use data from multiple previous frames. These examples will just constrain us to one. So frame number 3, after I've decompressed frame 2, I use the result to predict some values in frame number 3. Frame number 3 cannot refer directly back to frame number 0, though. If you want to implement such a thing on assignment 5, that's a good source of marks, though. That would be a good advanced thing to implement. You have to implement p-frames as a basic thing, but implementing a p-frame that can refer back to multiple previous frames would be an interesting advanced thing to implement. Of course, doing so requires the decompressor to keep more data around, and it means that there's more data that needs to be intact for the p-frame to be successfully decompressed. So if you lost some earlier data, then you might be in trouble. So an example here is, if I only tune in to the stream here, I don't have frame 0, I can still get frame 1, 2, and 3 if I start receiving data around the time frame 1 starts. If frame 2 referred back to frame 0 and frame 1, then I'm out of luck. I can get frame 1 if I tune in here, but I can't get frame 2, and that's one thing to consider. So in Mpeg-1, the prediction only used the previous decompressed frame. So p frames only went back by 1, and our baseline for assignment 5 is the same. And so, just to be clear, a p-frame is any frame that contains any blocks that use this prediction, that are stored via delta compression. You don't have to store every block in a p-frame that way. So you could have some blocks that are stored from scratch, if it makes sense. And we'll talk about reasons why it makes sense in a few minutes. So yeah, they can contain some blocks that only use the intra-block compression. They only use data from inside of the same image for compression. A general rule of thumb, and I'll get back to this later, is that we should expect that a p-frame requires about 10% as much space as an I-frame. So an I-frame has already been compressed. It's been compressed as its own image. A p-frame should require about 10% on average as much data as an I-frame does. So we can see that there's a benefit, therefore, to using a lot of p-frames if we can. Then the question is, and this is a weird one, we have to go in a lot of directions with this. Why am I only allowed to use the previous frame to predict the next one? So I'm in frame 3, and frame 3 has a lot of similarities to frame 2, but it's got some similarities to frame 4 as well. Why can't I use frame 4 as a source of information for frame 3? And you might be wondering, why is that relevant? Why would I ever want to do that? Why could it have similarities to a future frame that it wouldn't have to a previous frame? And so think about it like this. Here's 3 frames. And they all have the same background. So I don't know, there's some trees or something. There's some nice coniferous trees. They all have that. And that's fine, because that means that here's frame 1 and here's frame 2. I gotta finish drawing the tree. And then there's frame 0. Well, that means that if I need to predict frame 1, I can always use the tree, the data from frame 0. But what if there's something in frame 2 that's in frame 1 but not in frame 0? So something comes into frame here. An object begins to enter the frame. Well, I could take some of that data out of frame 2 if I'm allowed to look into the future. It's not in frame 0, so I can't just use the previous frame to do that. If I'm allowed to grab things from both of the past frame and the future frame, maybe I can get more compression. Maybe I can do more delta compression or more accurate prediction. And the more accurate the prediction is, the more likely I get better compression. Okay, so that's one reason why the future data could be useful. The next question is, how the hell am I supposed to actually do that? How am I allowed to look into the future? Well, I am, and you'll have to bear with me for how I'm allowed to do that. So an example being this. This sequence of frames is slowly fading to black. So frame 1 is pretty much exactly halfway between frame 0 and frame 2. If I predict frame 1 based on only frame 0, every pixel is a little bit darker. There's a difference. What if I'm allowed to predict frame 1 based on the average of frame 0 and frame 2? Well, it's probably a lot closer to the average of those two frames than it is to just one of the two frames. And we know that the closer it is to its predicted value, the smaller the delta values are going to be, and therefore the more compression I could achieve. So if I'm allowed to use both the past and future frames as a predictor, I might get better compression. And if I do that, I end up with what's called a B frame. So the idea behind the word B is it's bidirectionally predicted. I'm allowed to use data from a single past frame, a single future frame, or both, or neither. So just like before, I could have certain parts of my B frame be intra-block coded. So just coded based on their own information, not from other frames. This creates quite a bit of complexity. Adding B frames, therefore, is you have to have P frames in assignment 5. Adding B frames to assignment 5 is something that would get you quite a bit of extra marks as one of the advanced components. So to avoid circular dependencies, we first have to restrict that a B frame can't depend on itself, obviously, and therefore we can achieve that by forcing every B frame to depend on the next and previous I frame or P frame. So here's a B frame that depends on this, and it depends on this. But it can't depend on this because that would mean we could have a potential circular dependency. So every B frame depends on potentially the previous non-B frame and the next non-B frame. Now we also have to have a constraint on the way P frames work. We don't want a P frame to be able to depend on a B frame because we could also get if this was allowed to happen, we would have a bit of a problem because the P frame now depends indirectly on itself, which we can't allow to happen because that would be impossible to decompress. So typically what we do is we say an I frame is a standalone thing, a P frame depends on the last I frame only, and a B frame depends on the previous and next P frame or I frame only. They can't depend on other B frames. But if you think about that, if we define that set of restrictions, the existence of a B frame is possible. We don't have that issue of how do we see into the future. Because if I first reconstruct the I frames, and then I reconstruct the P frames based on the I frames and the other P frames, then I have all the data I need to reconstruct the B frames. So this is possible. So I can have all three of these types. And Mpeg-1 supports all three of these types. Now, B-frames do create a bunch of other issues. And one of them is, in my previous example, if I wanted to send you this data, I would just send you the frames in order. I'd send you frame 0, then frame 1, then frame 2, and you could reconstruct frame 2 based on frame 1, which you already have, frame 3, which you can reconstruct based on frame 2 that you already have, and so on. I can't really do that here. I send you frame 0. If the next thing I send you is frame 1, you can't do anything with it. You have to wait until you get frame 3. That's sort of annoying, because what if frame 3 isn't going to happen for a while? So there is a bit of an issue there. Whoops, this should say AVC. So this is H.264. H.264 allows you to have a B frame depend on multiple past frames and multiple future frames, or a combination of the two. And as I said, we do have to define some rules about when a frame can depend on other types of frames. So I are standalone, P frames depend on P frames and I frames, and B frames depend on P frames and I frames only. And in general, a P frame or B frame depends on the most recent I or P frame. So for example, this B frame here can't go all the way back to this I frame. It goes back to whatever the most recent P or I frame that occurred was. And the same thing is true of the future. So because we can't decompress certain B frames, like frame number 1, I can't decompress frame 1 until I have frame 3. I know that when I get frame 3, I'll be able to decompress it just fine, because it'll only depend on frame 1 or frame 0. But I won't be able to touch frame 1 or 2 until I'm done with frame 3. Well, they have a few options. One option is for the decompressor just to hold on to it. I send you the data for frame 1, and you just sit on it and wait. And you don't touch it until you get frame 3. That's possible. The difficulty with that is it's hard to know where a frame ends until after you've decoded it in some cases. If you think about the way our encoding works, often we actually have to do the decoding to know how long the encoding is. So what's often done is we reorder the frames. A compressor will reorder frames such that you receive them in out of order, but you receive them in an order such that whenever you receive a particular frame, you can always decode it at that moment. So notice here that I receive frame 3 a bit too early, but I can decode frame 3 as soon as I receive it. I just can't use it yet. So I decode it and I hold on to it. And the next thing I receive is frame 1, which depends on frame 0 and frame 3. So I can then decode frame 1 immediately and get it out of my system. And then I get frame 2 and I can decode that and I can get it out of my system. And then finally I'm ready. I already have frame 3 and I stick it here. I actually send it out at this point. And then I get frame 5 and I hold on to it. And then I decode frame 4 and then I send out frame 5 here. So I typically transmit the frames out of order. I could also notice that the order can vary, and how to reorder them is a question of what the most convenient mechanism for the compressor is usually, or maybe what the decompressor would do. So here I could transmit it this way, this would work. I could also do it this way, where I transmit P frames a bit too early in some cases. I think this is the most natural way of doing it because of a reason we'll come to in a minute. But basically, I only ever need for B frames the two most recent, the two adjacent I or P frames. And if I arrange it so that they're transmitted in this order, I only have to keep track of in the order that I receive them, the two most recently received I or P frames. So what I mean by that is I receive frame 0, I receive frame 3. And that means I currently have two I or P frames on hand. Then I decode frame 1, I decode frame 2, then I receive another P frame. And then I can throw away the oldest of the I or P frames that I have. So if I do it in this order, I only keep around 2 non-B frames at any given time. But there are multiple orders that would work. There are also orders like this one where, notice how frame 6, nobody needs frame 6 yet. But transmitting it extra early might make it easier for me later because maybe I do need it for something and I don't know yet. So I can transmit it as early as I have it, pretty much. So to do this, the decompressor does have to maintain sort of a buffer of frames in progress to keep all these out-of-order frames until they're ready to be sent out, but also to have them around in case I need them to compute some sort of a difference. So in a scheme like this one where only one future frame and previous frame can be used by any given B frame, if I do it in this order, I only ever have to keep the two most recently transmitted I or P frames. I can throw them away as soon as I get to the next one. So yeah, in this example, as soon as I received frame 5, everything I was saving from before frame 3 can be thrown away. And as soon as I get to frame 6, everything that I was saving from before frame 5 can be thrown away, because no future frame that comes in after this point could depend on anything other than these two. Although in this case, because frame 6 comes after frame 5, nothing would even depend on frame 5 at that point. And so actually there's also the rule that once the frames are back in order, once you begin to observe a monotonic order again, you can throw away everything from before the oldest P frame that you have, or I frame. So this creates, even if I have an ordering for my decoding, it creates a different problem, which is that if I have too many B frames in a row, I'm going to have to save up for a long time. I mean, maybe I'm getting only 30 frames per second worth of data from you, but if there's 60 B frames in a row, I can't decode anything until you send me that P frame at the end. And so schemes, there's no remedy to this besides either waiting for a long time or setting a limit. And schemes typically set a limit of maybe 2 or 5 or 100 or something, some sensible limit, usually less than a second worth of data on the number of consecutive B frames. I think Mpeg-1 typically sets sets a limit of 2 B-frames in a row. But still, we'll see, 2 B-frames in a row is saving us a whole ton of data compared to using a P-frame. And so in assignment 5, if you get to B-frames, certainly you'd want to set a reasonable limit like 2 frames or 3 frames in a row is fine. There's no reason to try to run to huge numbers. And we'll see that if you do that, you can get much better compression, but at the expense of a lot of other things like the ability to seek through the video or to catch up on a stream if you pick it up midway through. One of the challenges I have is that Mpeg as a standard, well, there's a couple of problems. As a standards document, we saw with JPEG that thing where they suggested quantization matrices, and to cover for themselves, they said, we don't think these will necessarily work for any purpose. Mpeg as a standard doesn't want to make any firm statement. It's also true that the standards body that issued Mpeg will charge me $150 to read the standard. I can't actually get a hold of a copy of it without paying. And I don't think that validating this one statement is worth paying the $150, even if I'm paying it out of an expense account or something, so I didn't. That's sort of annoying. A lot of pieces of work that refer to the Mpeg standard, however, so I'm going to present this evidence as hearsay, a lot of pieces of work seem to indicate that there is this rule of thumb. Mpeg-1, generally we should expect that we use about 1 bit per pixel on average for an iframe, 0.1 bits per pixel for a p-frame, so about 10%, and 0.015 bits per pixel, so 15% of a p-frame for a b-frame. That means if I can use a b-frame instead of a p-frame just once, I'm saving 85% of the storage. So I want to use as many B-frames as I can if I have them. I've given at least one citation to some actual authors that are experts, apparently, in a published peer-reviewed venue that have said this is a rule of thumb. But if you go looking for it, you'll discover lots of pieces of work in literature that do refer to this exact distribution. So it does seem to be taken as orthodoxy by some large subset of Mpeg-1 people. This, I hope, proves that having support for B-frames, which can rely on any combination of the previous and future I or P frames, or both, can significantly reduce the storage requirements of a frame. Now, we haven't really spoken about how exactly we compute the values in a P frame or B frame, so we should talk about that. So let's just use this simple notation here. So the value, now, another issue is that we'll store each of our 3 color planes separately. So at any given time, if we're working with a frame, we're only working with one color plane, like the Y channel or the CB channel or something. So we'll just call it as a generic term V. Suppose I'm working with some color plane, like the Y plane, and I know the value of that color plane in the previous frame, and I know what its predicted value is in the current frame, or I want to produce the predicted value. So suppose that in general, V sub xy, superscript I, is the value at pixel xy for whatever color plane I'm working with in frame number I. The first question is, suppose I decide that frame number I is going to be a P frame. What do I store? Well, the basic way of doing this, the most basic P frame I can compute, I just take the difference of the pixel in this frame versus the previous frame. So all I do is I subtract vi minus 1 from vi at the same coordinates. And then the decompressor, which by the time it gets to frame I, will have frame I minus 1, it can reconstruct it by just adding that value back in. Now, there's a quirk here, which is that, wait a minute, will the decompressor really have this? Well, not really. The decompressor will have the decompressed version of this pixel, which might be a little bit different. So we need to control for that. There could be some error in the version the decompressor has on hand. And it turns out we actually have a pretty natural workaround to that. So here's what you would typically do to encode an iframe. We would divide the image into blocks, 8 by 8. Even HEVC uses 8 by 8 blocks. It also allows bigger or smaller blocks, but pretty much it defaults to 8 by 8. And Mpeg-1 uses 8 by 8 blocks. So we divide the image into 8 by 8 blocks, we compute the DCT, we quantize with some criteria, round it to an integer value. We then store it using some combination of delta compression and entropy coding, and then the encoder does this. The encoder takes the compressed frame and decompresses it itself. That way the encoder knows exactly what the decompressor will be working with. The encoding process for a P frame is similar, but keep in mind, I compute the difference between this frame and the previous one. I do that before I take the DCT. So the matrix I end up using as the input to the DCT is a matrix of differences. And that's significant because it means, of course, those differences probably have smaller magnitudes, and that means the DCT can actually likely be more effective if I'm lucky, if I have a good match. So I divide the image into blocks. Inside of each block that I choose to be a predicted block, because some blocks I could just store from scratch, but if I choose that a particular block will be predicted using the previous frame, I subtract the value of each pixel from the previous decompressed frame from the values in the current block. Then I take this matrix of differences, compute the DCT, round it to integer values. And then, just like with the encoder, I guess I should add an extra bullet point here, just like in the iframe case, I want to decompress the result. I want to know exactly what frame the decompressor looks at when it's done, so that I, the compressor, am able to better estimate the error the decompressor is working with. So just to be clear, again, I keep saying this, just because you're in a p-frame doesn't mean every block has to be a predicted block. But we assume if you've decided to make a p-frame that some blocks are. Also, there's no requirement that any particular frame be a p-frame. There could be cases where a run of 150,000 consecutive frames are all iframes. It's the compressor's choice when to make an iframe and when to make a p-frame. So what about this business? Why is it that I'm not actually computing this? I don't compute the difference between this pixel and the one in the last real frame. I compute the difference between this pixel and the one in the decompressed version of the previous frame. So what's going on there? I have an example. I fiddled with this example for a while. I don't think it's to my liking yet, but I think it has enough information that it may be tough to read, but I think the point is there. So here's a frame. And suppose it has fractional values. So this is presumably, I guess I've done the DCT already. Let's not worry too much about that. But suppose I have this set of values, whether it's image data or not, who cares? I quantize it. I have the quantized frame now looks like this. And then the decompressor takes the quantized data, multiplies it by the quantizer matrix, and gets this. And this isn't the same. So there are some errors. So the error between this and this isn't very big. The error between this and this isn't very big. The error between this and these two things is a little bit bigger, but still not that bad. And we expect to get that kind of error. We know that's the price we pay when we use quantization. Okay, so here's frame 0. Here is the decompressed version of frame 0. Okay, so I've just put them here. Now suppose that this is frame 1. And notice that frame 1 has a lot of similarities to frame 0. They are pretty similar. And there's my quantization matrix just like before. So suppose that I want to store frame 1 as a p-frame. And I compute the difference using the actual original value of frame 0. Okay, so here's the difference matrix I would come up with. I take the difference, I quantize it as normal, and then the decompressor decompresses it. But what does the decompressor use? Does the decompressor actually have this frame? No, it doesn't. The decompressor only has what it got for frame 0. So the decompressor takes the differences and then adds back it undoes the quantization, and then it adds the value of its own frame 0, which is a bit off because frame 0 had some errors. And here's the error per element. That's tough because that means any error that got encoded into the representation of frame 0 hangs around in frame 1. That error is going to follow me forever. If I have one iframe and there's some error in how I store it, and that's followed by a sequence of an arbitrary number of p-frames, whatever error was present in this iframe is going to persist and compound with each p-frame because there could be error involved in this quantization. I don't want the error to pile up. I want to have as many p-frames as I need in a row and not have the error pile up too much. And the issue is basically there are some errors I can't avoid. Obviously, I'm going to have quantization error, but I know that the decompressor doesn't have this information. So if I compute delta values, I shouldn't use this information either. I should say, what can the decompressor reconstruct? I want it to get something as close as possible to this. I know that it has this. I, the compressor, can determine the decompressed version of frame 0. So what I'll do is I'll compute the difference of this, from the decompressed frame 0. So if I do that, I get this matrix, and the error ends, and the decompressor does the same thing. It takes my quantized differences, reverses the quantization, and then adds them. So for example, to reverse this will be multiplied by 2, so I'd get 6. 6 plus 32 is 38. 2 multiplied by 4 is 8. 8 plus 16 equals 24. And then these are both zeros. So the decompressor undoes the quantization and then adds in its own values from frame 0. But I knew that when I was compressing. I deliberately used those values to take my differences. And then it gets this decompressed frame with this set of errors. So let's just quickly compare this set of errors with the errors on the previous slide. And the errors on the previous slide are a combination of the errors that would naturally, some of these errors are less than 1, which makes sense because I'm just getting rounding errors. These are I still get error because I'm naturally going to have errors from quantization, but these errors are unique to this frame. They're not the result of the errors in frame 0 plus the errors in frame 1. So that's a deliberate choice, and if you don't do that, you will notice the errors pile up really quickly and your video isn't very watchable. So always take the deltas with respect to the decompressed version of the frame, not the original frame itself. Of course, doing this means that the compressor now has to decompress everything that it compresses. It has to, as it generates each frame, also decompress that frame so it knows what the decompressor has. That adds computation time to the compressor. It doesn't add any computation time to the decompressor, though. And we'll see that, if something has to be slow, it's better that it's the compressor, because we're more likely to compress once and decompress many times, and we're more likely in the typical streaming video case to have more computational resources on the compressor side. So maybe I'm compressing in advance, in which case I can just take as long as I want and then save my file and decompress it later. Even if I'm doing streaming compression, I can pay extra for a good quality streaming compressor, for a machine that can run my compressor at high speed. Whereas I might be decompressing on a phone or a watch or something. I want the decompressor to be fast in any case. Let's talk about another issue that shows up that can help us save some bits. So here are 3 frames that I've made up, basically. Notice that they are distinct. They are similar. I mean, clearly there is a high correlation between them. But the correlation isn't just temporal, it's also spatial. That is to say, this bit here is located down here in this image. They're both there, but they're not the same place. So even though, the sequence shows movement, which means that obviously the pixel at this location here doesn't match up with the same location in frame number 1, but the same value is still there. Ultimately it might just be displaced a little bit. So I have a highlight here because I knew my drawing wouldn't be so obvious. So suppose I compute frame 1 and frame 2 as p frames. Well, the way I would do that with our naive calculation from earlier is I would compute the deltas for this block by taking them with respect to the same pixels in the previous image. So I subtract this, sorry that this isn't very visible, from this. And we'll notice that that's going to result in maybe some of this, like this bit here matches up with the corresponding bit over there, but there will be some delta values that are really large, like this middle bit, which is the bright sky against a sort of the green of the pear. If we have large delta values, we get bad compression. Who knows? It might even be, maybe this block is actually, if we're doing it this way, it's easier to compress it from scratch with Intra coding as opposed to taking the delta values. So I want to avoid that. So in this case, if I just take the difference straight up between equivalent pixels, they don't match up very well because the frame has changed. But it hasn't changed that much. So much information is in all 3 of these frames. The same information, just displaced a little bit. So for example, if I want to consider this situation here in frame number 2, I could observe that the block in frame number 2 does exist in frame number 1, just not the same place. It's sort of up here. And in frame 0, the same thing is happening. It's sort of up here. So if I want to compute deltas, I don't want to do them pixel by pixel. I want to find some way of saying, hey, I want you to shift the whole block up a little bit and take the difference with respect to where you end up, not just with respect to the same position. And so in this case, what's happening is the global movement of the frame has affected where the block's pixels are. Now, what I'm describing, the slide gives it away, motion compensation isn't just for global movement. There are plenty of cases where maybe only part of the frame is moving, and maybe 2 different parts of the frame are moving in different directions. So it's not like I can just find some global offset of the image. Maybe the particular feature I'm looking at moved in one direction, but the rest of the image moved in a different direction. If I zoom in on those blocks, if you look at them, they look very, very similar. but it could be that there are some minor differences. So I'm I know in advance where they are. I think one of the blocks is displaced a little bit vertically. So I think actually if we draw a line across, do I actually? No, I don't. I think I had a second graphic I made up which drew lines across. The blocks aren't identical. So the delta values are still, even if I take them with respect to the offset blocks, they're still not going to be all zeros, but they'll be probably very close in most cases. Like, I mean, most regions, except for on the boundary, most regions do match up pretty well. So what we're talking about is something called motion compensation, which is I want to compute delta values, but I don't want to use necessarily exactly the same location in the previous frame. I want to choose an offset. And we typically call this offset a motion vector. So in this case, I'm encoding this block here, the one outlined in solid red. What I want to indicate is I want to take it as differences with respect to a block in the previous frame, but I want the differences to be in a block that's been offset by this vector here. I'm just coloring in something that's already black. This will be this position here. I'll just draw this on. This is the position x comma y, the top of the block. And this is x plus some delta value, and this is y plus some delta value. And what I want is a motion vector v that tells me those delta values. That's it. And we can observe that maybe the motion vector for particular parts of the image can be different because some parts of the image move in different directions or at different speeds. But I want the ability to specify an offset for when I take my differences to compensate for motion inside the image or the global motion of the entire image. So I want to search for a motion vector. And in general, I suppose the ideal motion vector is one that finds the real location of the block in the previous frame if it exists. But in any case, in practice, the motion vector represents the displacement between a block and the best match, whatever that means, for the block in the previous frame. And so we usually define these motion vectors at the level of an entire block because, we could define a single motion vector for every single pixel. The problem is we have to store the motion vector for one thing, and it's going to be difficult to find it. So we typically store one motion vector per block, or maybe per macro block, which I'll talk about in a few minutes. So when I have a motion vector for a block, every pixel inside of the block, we compute the differences by taking the value of a particular pixel and subtracting off the value of that pixel, an offset pixel offset by the value of the motion vector in the previous frame. Now it's true that, every block, so I've got this set of blocks. There's one block, there's the next block, there's the next block. I've got these set of blocks. The motion vector for this block points up here. The motion vector for this block, hey, wait a minute, probably points somewhere similar. If the frame has motion, these are only 8 by 8. Two adjacent 8 by 8 regions probably have relatively similar motion vectors. Not the same, but similar. And so typically motion vectors are compressed with delta compression of their own, where we only store, instead of, if we have two adjacent blocks with motion vectors v1 and v2, we don't store v1 and v2 directly. We instead, store the motion vector for the first block and store every other motion vector as a difference from the previous one. The idea being that they're probably, more often than not, likely to be similar. Now remember that there's no requirement that you use motion compensation in general or for a particular block or that a particular block be predicted. It's true that if you support motion compensation, there's no harm in using it. There's never really a case where computing the difference using the naive method is any better than using motion compensation because you could always have a motion vector which is all zeros. And for the assignment, you should have some kind of motion compensation. But remember that you don't have to use it on every block. There could be some blocks where you need a motion vector of 0 or where you just store the block using intra-block compression. You don't use a prediction technique. So let's take a look at these two things. Suppose that I make this frame a P frame and this frame is an I frame. Or another P frame, who cares? But suppose that frame number 1 is, frame number 1 is a P frame. First observation, these two images are basically different. This is not motion. I do not see motion between frame 0 and frame 1. If I do see motion, it is such exaggerated motion that there's no real similarity between them. They are two basically distinct images. They have similar subject matter, But who knows why that is? They have similar regions of the same colors, but who knows why that is? They are different images. Here's the question. Suppose for some reason I choose to make frame 1 a p-frame. Normally, the logic is if you discover that two images are too different, you just store an iframe. Don't bother with a p-frame. But suppose you try and store frame 1 as a p-frame. What should I use as the motion vector for this block in green? Well, I mean, there's no movement. I mean, that area, this region, doesn't exist in the other image. So what do? Well, let's go looking for the block, the region of the other image that gives us the smallest differences. So what I want is a region with a greenish area down in these three quadrants and sort of brighter or maybe dark up in the other quadrant. So again, we're not actually trying to compensate for real motion here. The point of a motion vector is just to make your delta values small. You just want to take the difference between this block and another area of the previous frame that gives you small delta values. So what if I choose this area? So again, it's got sort of a greenish thing happening down in this part, and up in the other corner, up here, it's got sort of a dark bluish, I guess. It's not perfect, but it is a pretty good match. I mean, if I have to choose a match, maybe it's that one. It's got the greenish thing in three quarters of it and sort of a darkish area up in the other corner. So if I chose this, even though it's a coincidence, I might get relatively small delta values. And that's the point of a motion vector. That's it. It doesn't actually have to model real motion. The motion vector, just to be clear here, the motion vector is, the block I'm looking at is in this area. So the motion vector is this, as the diagram shows. And so the issue with this is actually sort of scary, because in our original example where we were modeling real motion, it was reasonable to assume that there's not very much motion. That is to say, if I have two frames 1/30th of a second apart, they represent a relatively small move. In fact, actually, this is a contrived example. This is too much movement. If you think about this being a total of 1/10th of a second, you wouldn't, as a human, be able to even see the pair at that point. You're going so fast. The motion would be much more subtle if you were actually doing a pan across this pair. And so that means that if you're compensating for real motion, you probably have very small motion vectors that are pointing only a couple of pixels away. But if you're just looking for the best match to take differences against, it can be literally anywhere. It can be halfway across the image because it doesn't actually have to be motion, just a good choice of a block to take a difference against. That's sort of scary because then we have to begin thinking about questions like, how do we compute the motion vector? What's the best motion vector? Now, as I said earlier, just to cap this off, really, if you're computing differences and you discover that every block is really different from the previous image, it's probably better just to call it off and store an iframe, not to try and use a p-frame. Certainly, if there are blocks that don't have a good match in the previous image, just store them as intra-coded blocks. Do not try and store them as differences. It might actually result in worse compression than just storing the block compressed from scratch. So we have an image that's 1080p. So it's got 2 million pixels. I want to make one motion vector per block. But the motion vector can point, the motion vector basically tells me where is the top corner of the displaced block. It doesn't have to be lined up on a block boundary. It can be anywhere. Anywhere that there is an 8x8 region that matches the block pretty well. But that means that the motion vector can point at any pixel in the image. And there are 2 million pixels. And each time I compare a block to a candidate block with the motion vector, that's 64 comparisons. That's a lot of work, and that's for every single frame, and there are 30 frames per second. I usually do not have time to try every possible pixel. Now, of course, our usual remedy to that is construct a clever data structure that lets you do searching. But I need to construct the data structure again for every frame, and that's not going to work either. The data structure takes too long to build. So I'm going to throw this in there in the middle. If I use 8x8 blocks, so here's my image. If I choose, here's my first 8x8 block in the top corner. At the image's regular resolution, this 8x8 region corresponds to one Y block. But if I use 420 subsampling, the first 8x8 block for CB and CR is actually this big because the whole image gets scaled down, right? So a single 8x8 block in the input image refers to one block of Y pixels and 1/4 of a block of CB or CR pixels. And as a result, there's a bit of a misalignment. And so Mpeg talks about what are called macro blocks. So a macro block is 16 by 16. And it consists of, obviously, 4 8x8 blocks. And each 8x8 subblock is one block of Y pixels, but the entire 16 by 16 macro block corresponds to one block each of CB and CR. And that means if you talk about a macro block, you are talking about 4 Y blocks and 1 CB block and 1 CR block. And often operations in the Mpeg and other compressors, but the Mpeg family, are done per macro block. So you might compute one motion vector for every macro block, not one for each 8x8 block. Computing it per macro block also means you can reuse the same value for the color blocks as you do for Y. I find one motion vector for this huge macro block, let's say it points over there, I can then use that motion vector when I'm encoding the 4 Y blocks and when I'm encoding the CB block and the CR block that correspond to this 16 by 16 region. And so other aspects like whether a particular block should be predicted or not, whether it should be a P block or a B block inside of a P frame or B frame, those might also be done on a per macro block level. Okay, so that's one thing. That's just an aside. It's your choice how you compute motion vectors, but the question then is, how do I compute the best one? I have a block. I want to find the best match, the one that results in the smallest delta values in the previous frame, or maybe in the previous frame or next frame or combination of the two. So the issue here is that there's actually a lot of fighting constraints. The first one is we're not actually compensating for real motion in some cases. I just want a good, like I had with the fruit bowl here, I just want a good match. I just want to have small delta values. That means as well, I don't even need the one that looks the most similar to my current block. What I need is the one that results in the smallest storage being used. And that depends on how I store the block. If I use this particular form of delta compression, certain delta values might be smaller. If I use Huffman coding, I get the same weird feedback loop that Deflate has. And we saw in Deflate that in some cases emitting a back reference that goes back further with a larger distance actually takes up less space than a back reference of the same length at a shorter distance because of the weird nuances of Huffman codes. The same feedback loop sort of shows up here. I need to find a motion vector that gives me the best delta values, not necessarily the best possible block in terms of similarity. I also have to figure out what does it mean for two blocks to be similar. I have to choose some measurement of whether a particular motion vector is good. That's a bit of a tough one too. And so I'm actually going to suggest some possibilities. Which one you use is more a question of what scheme you're using to store the data. So here are some options. We've got if I have the pixel value in this block denoted by Bij. So I've got an 8x8 block, we'll call it B, and B00 is the pixel at the top corner of the block, and B77 is the one at the bottom right. And then P is the entire previous frame. So we're talking about one block here, but we could actually have the motion vector point halfway into a block in the previous frame. So what I could do is I could compute the average difference between two pixels. So if I want to use that as a measurement of difference, I would take the absolute value. So that's the average absolute difference. I could compute the maximum absolute difference. The idea there being that big delta values are no good, and I want to make sure that the biggest delta value I'm storing is as small as possible. Although that could discount the fact that if I have a small largest delta value, it could be every delta value is that big, whereas a small average difference means that in general I'm getting a small value. And again, this depends on the relative encoding lengths of my delta values. If they go up linearly, then this is probably the best choice. If they go up quadratically or something, or logarithmically, I have to make different choices. I could also use the mean squared difference. Now, if you're computing these for comparative purposes, so if you compare two vectors by computing this quantity for both of them, keep in mind you can actually do some shortcuts. Because the block size is constant, so usually it's 8x8, here I've had it be B times B. If the block size is constant, then you can avoid even ever computing this. 1 over b squared, because you know that if you're comparing the value, this value for two vectors, that constant is in there for both of them, so you could avoid that. So there are some ways you could optimize this. I'm not even going to take a side here. I would probably start by using either this or this, and then I'd play around a bit if I was trying to choose a good vector. But even if I define a measurement, there's still a question of, if my image has 2 million pixels, I can't test, I mean, even if I have lots of time for compression, I can't expect to test all of them for every frame. So what do I do? And this is a tough one, because the behavior of these three functions, there's no way we can boil this down to some simple like gradient descent algorithm or something, because we don't know anything about our images. We don't know that the previous frame has any particular pattern to it. So if we try a particular vector and it's bad, that doesn't mean that the best possible vector isn't right next door. So instead, we have to basically either make assumptions or spend tons of computation time. And so it's worth considering that if we have an asymmetry, it's of course important that the asymmetry be that the decompressor is fast and the compressor is slow. We can't have the decompressor being slow because we need to be able to decompress in real time. And so if we have a case where our compressor has to take 10 times as long, but the difference in compressed size is huge, maybe it's worth spending that time, as long as the decompressor doesn't get slower. And it's worth observing that the decompressor doesn't have to find a motion vector. We just give it a motion vector. It doesn't matter how we found it. The decompressor takes the same amount of time no matter what motion vector we give it. So this operation of finding the best one doesn't affect decompression, but it does affect compression time. And we're going to need to choose some kind of a compromise between a scheme that always finds us the best one, so an exhaustive search, and a scheme that works quickly. So the key point here is, because the previous frame is essentially arbitrary data from our perspective, the only real way of finding the best vector is to try literally everything. And we really can't expect that we're going to do that. So assuming that we can't do that, which I'm going to assume, we need to find some alternative that gives us a good answer in a reasonable amount of time. And we do that by making assumptions. So one assumption, a pretty easy one, is I've got a block, and the block is, let's say, here. I will go looking a fixed radius around the block. I'll choose some delta x and delta y, and I will look at every pixel inside this region. What's great about this is that you can even do it with a benchmarking approach, where you start one layer and you keep working layer by layer, and you just decide when to stop based on how long you have. If you only allocate a certain amount of time for each frame, you just stop as soon as you're running out of time. And you crawl further and further outward. And the idea behind this is this will be very good at identifying local motion, for motion compensation for actual motion. So if your frames are moving slightly, or if your objects are moving slightly between frames, this will probably catch that if I use a sensible radius. But it won't allow me cases where, hey, what if the same thing for some reason is found over here, and I want this motion vector, and I just want it because it gives me good delta values. This won't find it. And so it still will. I think I'd recommend starting with this if you're playing with motion compensation, because it's easy to tweak and it's easy to parameterize it such that you can increase speed by decreasing the radius. The problem is if the motion is moving at really high speed, or if you have really low frame rate video, where if you're only going at like 5 frames a second or something, then it is reasonable the block could move by this much inside of one frame. But if it's high frame rate and you're working with actual motion, this is very likely to catch some of it. Now, the question then is, okay, what if I do want to find the best match in the entire frame? So one option is to do sort of binary search. This is a different style of diagram. When we do a search for a vector, we're only searching for a single point, and then we sort of shift the block onto that point to take the differences. So let's assume that this square here is some point, is some a vector that I'm testing. Here's what I will do. Who cares where in the image the block is? I will begin by testing the center of the image, like basically taking my block and overlaying it here, and then asking what let's say the average absolute difference is. And then I will fan out, and I will go, notice how if I do this, it divides the image up into 4 pieces. I will look at the center of each of them, not indeed unlike binary search. And then I see of these 4 directions around it, or maybe I choose 8 directions, I choose whichever one has the best match. Now this is dangerous, because just because if I go down here I get a bad match doesn't mean that the best match isn't, let's say, right there. I can't make assumptions about where a good match is based on a single data point like this. But I need some way of pruning my search. So suppose I begin by, I fan out in 4 directions at each step, and I get rid of the most, of the worst 3. So now I find this is the best match I've found so far. So I fan out in 4 directions around that, and I get rid of the worst 3, and I end up down here. And I just keep searching until either I find a match that's below a certain threshold of difference, or until the distance between locations is 0, because that means I've converged as close as I can get, and I've searched everything. And the idea there is that what I'll end up with is I'll search, my search neighborhood will become smaller and smaller until eventually it's 0, and then I do more searches in a more dense search in an area that seems to be producing good matches. So I converge on a good match without doing too many searches. The difficulty there is that this doesn't, if this were, let's say, a convex function or something, I'd be able to use a gradient descent method, but I'd have some options. I know nothing about the way this image actually looks, and if I just choose discrete locations to test, how do I know that my best match isn't here, and that I'm just missing it because these are just both bad places to start? So I don't know that, and that's a difficulty with this, is I can't make assumptions about the general structure of the image. One trade-off you could try is do the same thing, fan out in 4 directions, but instead don't throw away 3 of the 4. So always fan out a certain distance, like maybe 3 times. So I start here, I fan out once, I fan out again. Then I've now tested 21 points. So I've tested 21 points. Let's say throw away, I don't know, 2/3 of them or 3/4 of them, which may not be all from the same area. So I throw away a bunch of them, and then I fan out from those points, and I throw away a bunch, I throw away a bunch of those as well. And then I fan out again. So instead of just keeping the best point at each step, I keep the best 25% of my points. By doing that, I allow myself a little bit more leeway to maybe catch a case where the thing I was looking for wasn't at the local optimum. And then there's a few other heuristics. So one of them is just stop searching as soon as you find a good match. Don't even look for the best one. Just look for one that's good enough, and as soon as you find it, just quit. That way, and maybe the threshold gets higher and higher as you continue searching. The longer the search has been going on, the more you lower your standards, with the goal being to just stop the search and keep the compression moving. You could also, of course, start your search in whatever found you a good match for the previous block. On our logic from earlier that 2 adjacent blocks likely have similar characteristics, you could start your search, let's say your local search, from wherever the previous block's search ended, on the grounds that maybe if you use a cutoff, you might find a good match sooner. And then, as always, we can do randomization. We can do this in lots of ways. So to compute a difference with these difference metrics, we need to compute 64 iterations. That can be a bit tough, but we need that to get the perfect difference. Suppose you randomly don't compute some iterations. You get a difference that's off, but because it's random, you don't necessarily get a difference that's biased in any particular way. And you can save a few computations by doing that, assuming you can generate random numbers quickly, which isn't always easy. And you could use pseudo-randomness, obviously. But you could also do that to decide whether to search a particular location. So for example, if you use a pruning approach like this, whether or not you actually go here could be determined randomly. And the idea behind the randomization is it doesn't mean it's any less likely of you hitting any specific place, but it does reduce your the total number of searches that you do. So randomization is always an option to try and speed stuff up. And then I've got one last thing to talk about, which is stream recovery, which is a common issue because I might be sending millions and millions of frames of video, I'm broadcasting continuously, and you don't physically tune in. Your decompressor doesn't start receiving information until, let's say, here. You tune into the stream here. So the question is, what happens? Well, clearly, if the first frame you actually receive is this one, you can't decode it. You don't have the entire P frame that it refers to. If I only received half of this, I can't decode the B frame. I can't even decode this P frame because it also depends on that. So maybe my decoder, if I just tuned in, can't see any of these frames and has to wait until the next I frame before it can pick up the stream. So we haven't talked about this before. I did spoil this earlier in the lecture, so I'm going to skip over these slides. But it is relatively normal to pick up a streaming video stream halfway through. and to still expect to be able to watch it and not to wait too long. Now, we're used to having to pre-buffer a little bit, so I don't mind if I have to wait a couple of seconds. Maybe I miss 60 frames, but I want to be able to tune in and relatively quickly begin watching the video and get all the full benefit of watching it. I want all the audio, all the video, every single frame. I might need a little bit of lead time for that to happen, but I want to be able to pick it up. So it's one thing to say, hey, that's right. You can't, if you tune in midway, if you tune in, let's say here, you can't see this, you can't see this, you have to wait for an iframe. But it's also that you have to design a bit stream where even if you pick it up halfway through, it's obvious to you when you're at the beginning of an iframe. So you know, here's where I can start decoding. So if all you have is iframes, it's easy to pick up the stream as long as you design the bit stream such that every iframe is easy to pick up. So obviously in the middle of a bit stream, you can have any sequence of bits. If you design a bit stream so that a certain bit sequence, I don't know, like an obvious one might be this, 0xFFFF, only occurs at the very beginning, the first little bit of an iframe, then when your decompressor picks something up halfway through, you just go looking until you see this. And the first time you see this, you say, this must be the beginning of an iframe. So you try decoding it like an iframe. But then you say, well, what if that sequence appears organically? What if it's in arbitrary data? Well, if the decompressor tries decoding it like an iframe and then gets a garbled mess, it quits and looks for the next 0xFFFF. And hopefully it eventually picks up the beginning of a real iframe. Once it's picked up the beginning of the stream, it's good. Although in practice, we typically design the stream so that you could lose it in the middle as well. With television reception, you could often have an error that occurs in the middle where you lose a few seconds of video and you have to pick it up again. But the idea is, in general, once you've picked the stream back up, you can stop searching. You just keep decoding at that point. Once you have p-frames, it's perfectly reasonable that if you pick the stream up, let's say here, you can't decode anything until you see an iframe. That's fine. And you might be familiar already. I think this came up when we were talking in one of the live sessions, what the Telltale Artifact for video compression with this kind of corruption is. It's where you see a strange corrupted frame where you can pick up on movement, but all the colors are wrong. That's the typical artifact of decoding p-frames without having the iframe that they went with. When B-frames are present, you've got all sorts of problems, one of which is that you don't really pick up the stream here because these frames arrived out of order. So if I pick up the stream here, the P-frame that comes after this hasn't been transmitted yet. So actually, this P-frame depends on something that came long before I tuned in. And so again, the usual rule is until you get to the next iframe, you can't see anything. An added wrinkle, though, is that if you have a situation like this, so I've got an iframe, and then I've got a B-frame, and then I've got an iframe, this would actually be, so this is 1, 2, and 3. This would be transmitted as with the iframes first. So it might be that the next iframe was already transmitted. If I tune in, let's say after 2 frames, I get a B frame that refers to 2 iframes that I haven't seen yet. And any P frames that come after that or other B frames might refer back to frame number 3. But in any case, I have to wait, if I tune in late, until the next iframe that gets transmitted to me. And so the way that we typically moderate that is because it might be a while for an iframe, we have to design a scheme, and broadcast schemes are careful about this, so that there are a certain number of iframes every second. So maybe 2 times a second or once every 10 frames. We want B frames and P frames because they save space. We want I frames because they allow us to pick the stream up if we lose it or if we tune in late. And so broadcast schemes typically require I frames in a certain interval, guaranteed. Even if you don't need them, even if the video is not moving or changing very much, you must emit a full I frame to wipe the slate clean every now and then so that anybody tuning in the meantime can pick up the stream. This is actually useful even when you're not broadcasting. Even if you have the entire piece of data, like it's a video file or something, it's still useful. Video editing is a big deal. You want to be able to see every frame, but actually just being able to fast forward. If I'm watching a video and I say, okay, I want to skip to this point. Well, you can do that if you have a video file, but you have to back up to the last iframe and then decode everything until that point. If iframes are like 10 minutes apart and you skip to the middle of a 10-minute segment full of B frames, your decoder has to decode 5 minutes of video before it can seek to that location, and that can be really frustrating. And so, again, if you're encoding your own video for your own purposes, who cares why you're doing it? Like, so, I mean, the seek time might not be a priority. But for media where people might want to seek, so consumer media like Blu-ray or streaming content to some extent, as well as broadcast television, typically we'd want to have iframes close together to allow easy seeking. It's true that streaming services have a compromise there, which is that they can be sending you video, like a YouTube video can be sent to you with very few iframes, and if you seek through it, it can just tell the server to resend with an iframe at the beginning. The server actually has the ability to maybe send you a different stream than it has internally, so there are some compromises that can be made there. And so we need the frequent iframes even in cases where we don't want to pick the stream up in the middle. Even if we have the entire stream, it is helpful to have frequent iframes. And doing so, of course, inflates the bit rate. I mean, if we have to emit an iframe twice a second and I only have 1 megabyte per second, then I'm going to have to use up a lot of that space transmitting these iframes. And so that's a trade-off. And it's one that you're welcome to exploit. You do not necessarily have to have lots of iframes in assignment 5. One of the advanced options is fast recovery. If you implement recovery, you probably want to have iframes regularly, but there's no requirement to do that. And of course, there's this question of, do we really need any iframes at all after the beginning? I would argue that the compression advantages you get by having only 1 iframe per hour of video are sort of don't outweigh having 1 iframe every few minutes. It's true that, yes, you do save quite a bit. I mean, an iframe is 10 times as big as a p frame on average. But on the other hand, if it's only 10 times as big and I have 1 extra iframe every, I don't know, minute, an iframe is 10 frames of it. So an iframe is 10 times the size of a p frame, so it's like 10 p frames. And 10 p frames is 1/3 of a second. If I have 1 extra third of a second of video data per minute, and in exchange I can do seeking much more easily, I think that's actually a sort of a worthy trade-off. So that's one thing to think about, but it is, of course, dictated a lot by the circumstances. If you need to be able to tune in at any point, of course you need iframes relatively frequently. Okay, so we've actually gotten through enough video compression that I can turn you loose on assignment 5. I'll post a separate video demonstrating the various sort of streaming video infrastructure I've created for the assignment, which I hope is a good trade-off, especially in a semester like this, where in a lecture I'd like to be able to pull up videos and we can look at the artifacts that compression creates, but I can't do that because any video I stream using Zoom or using this will of course be recompressed, and so any artifacts I point out might actually end up looking better or worse or whatever when I do that. So instead we'll have to use our imaginations. You'll see lots of video compression artifacts anyway because you're going to be writing a video compressor, and so there'll be a lot of learning on the job, I guess, for that.